This is lab number 4, Physics 2211, Oscillations, and my name is Tiffany Laij. Introduction. The purpose of this experiment is to measure and predict the motion of an oscillating mass and to compare this from a real-life model to a computational model. This is to analyze the energy in a system such as kinetic, gravitational potential, and spring in this experiment. In this lab, we will go over the physics concepts behind it, computational setup, analysis, and what-if questions. For this lab, we have a couple of physics concepts such as Newton's second law, which is the change in motion or the acceleration of an object is directly proportional to the force applied. Here, force is equal to mass times acceleration, or the change in momentum over time. Here in our system, we have different types of forces such as the force of spring and the force of gravity with the formula shown here. The net force is equal to the force of spring plus the force of the gravity. And this is how we're going to figure out where our object is over time using the velocity update formula that uses force to calculate the velocity at a specific time and the position update formula to figure out the position. Another fundamental principle that we'll be using is the energy law of conservation that states that energy can neither be created nor destroyed and only converted from one form to another. Here, the change in the energy of our system is equal to the work of surroundings plus Q. However, in this experiment, the change of energy is going to be zero due to the law of conservation. Everything is within our system. There's different forms of energy that is within our system, such as kinetic energy, the spring energy, and the gravitational potential energy within our system as formulas shown here. Here, when we add them all up, delta K plus delta UG plus delta US is going to be equal to 0, since there is no change in the energy within the system. The results of our labs and our findings. Over here, we have shown the graphs of the glow strip comparing the tracker software to the computational model. As you can see, they're pretty similar, but we will get more into that later. Procedure and experiment. So setting up the tracker using the video that's given, our system is going to be the oscillating mass, spring, and the earth, and the surroundings is going to be nothing. Our initial conditions is that the mass is 0.402 kilograms. Our position is as such, and it's going to be released from rest, which means there's no initial velocity. We're going to upload our video to Tracker, we're going to track the object's positions over time and take out the X and Y values and put that into our glow script so we can compare the real-life model to the computational model. And we're going to compare these graphs and draw conclusions. The video on the right shows our Tracker video, and on the left it shows that it's going to be calibrated from the fixed point in the video as shown. And the difference between the start of the mass and to the fixed point is going to be 0.7 meters. Computational model. So setting up our computational model, we're going to put our initial conditions, which is the mass of the ball, our position, and our velocity. And we're going to add our constants, the constants of gravity, the spring constant, and the relaxed length of our spring. And then over here, we're going to add the forces and position and velocity updates so we can track the position and the velocity over time. The force of gravity, the force of spring, and net force are added. And over here is the velocity update and position update formula. And in lines 130 to 132, since the spring force is not constant, we have to update the position of the length of the spring. And setting up our energy, here are the formulas for the different forms of energy as shown for kinetic, gravitational potential, and spring potential energy. And we add all of this to get our total energy. In our while loop for the predicted number of values, we have to find the energy over time, which is going to be equal to the kinetic energy minus the initial kinetic energy. And this is the same for the rest. Data analysis. Over here on the right, we can see the X and Y graphs for both the experimental and the computational models. Over here, you can tell that there's slight discrepancies in both the X and Y directions, but they're pretty similar for the most part. The computational model is usually ahead of the experimental, or it reaches a higher point. As you can see in the Y position versus time graph, the model has a higher amplitude than the experimental, which is the red. And so what causes these slight discrepancies and these differences? So some of them is that there's energy loss to the external force of air resistance and drag. We calculated that there was no surroundings, but there is in real life situations. And there might be human error in tracking, and the tracker software is not 100% exact. What ifs and what does it mean? Is the energy principle or the law of conservation of energy satisfied? The orange line labeled delta T is the change of energy over time, shown in our graph on the right. As you can see, the energy changes between the different types of energy, the gravity, the spring, and the kinetic energy, which means that they're basically converted through the various forms, but the change, the orange line, remains at the origin in 0. This means that the energy principle's conservation is satisfied. The sums of above the and below the graph will equal 0 once we add them all up. Second question is to estimate the oscillation periods. So we calculate the oscillation periods by finding when it reaches the same point and then calculating the difference between those times. As you can see here shown in the graph, I highlighted where these periods are. The estimation of the length of a period for the x direction is 1.615 seconds, while for the y direction is 1.519 seconds. They're pretty similar in size, but they probably differ slightly because the string stiffness may be different between the x and y directions, and that's why they may be different. Thank you for watching.